Hello everyone, this is Mrs. Lindsay Pereira. Today we are going to talk about some problem spots for derivatives. So the question is it possible to not be able to take a derivative at a point? Okay, well let's think about this just a little bit. Let's think about some graphical situations where we might not be able to find a slope at a point. Okay, so again, some things that we actually did with limits that might kind of ring a bell. A hole, an asymptote, a jump. So these are all referring to discontinuity. Okay. All right. So again, that's really kind of where we're getting those from. That's what they have in common there. So again, this might be a situation where we can't find slope at a single point. Okay. So does that mean that if a function is continuous, that it is also differentiable? And the answer to that is no. Okay, well, why? Continuity does not imply differentiability. Okay, so let me say that again. Continuity does not imply differentiability. However, differentiability does imply continuity, so the reverse is true. Okay, so why is this? Why are there reasons that we don't have a derivative? And again, some of them we literally just talked about. Discontinuity, so if we have a hole, a jump, asymptote of some sort, vertical asymptote. Okay, but then we have other ones that we really kind of haven't talked about yet. It's called a corner. So the graph of that might look something like this. And again, I'll go over these in a little bit more detail here. So this would be your corner here. Then we have what we call a cusp. And this kind of looks like, I don't know, how the old-fashioned way of drawing like a bird right there, if that makes any sense to some of you. That would be a cusp. And then a vertical tangent. So something like if you have a graph that looks like this. Let me use a different color here real quick. And we'll kind of go through some examples of these. So if you have something right along through like this, you have a vertical tangent at this point here where you're trying to find it. So that would be undefined at that vertical line. A good example of that would be y equals the cube root of x plus 4. And in some of our examples we have coming up here, I'm literally just going to show you the graphs of them so you can see what they actually look like. So if you do want to grab your calculator, if you don't have that, you might want to pause your video because we're going to graph just a few of these. And again, just to show you what it looks like to be some of these things. But these are some reasons that there isn't going to be a derivative. Again, we talked about discontinuity quite a bit in our last unit, and these other three are the new portions. Okay, so here's the first example. Now I went ahead and I've actually graphed this, but you're graphing f of x equals the absolute value of x. We're not actually going to do the limit of this. Those are some good examples though if you do want to try them. I'm just really kind of referring to, okay, why can't we find the derivative at certain points? And this is an example of what we call a corner. So right here on our graph, this point would be what we call a corner. So at x equals 0, there we would not be actually be able to find the derivative. Okay, so that would be a corner. Our very next one, again, just kind of talking about reasons we wouldn't be able to take the derivative at a point. So f of x equals x raised to the 2/3. This again is an example of what we call a cusp. So this point, so you can see it's a little more curved here, but that would be your cusp. Okay, so again, if you're thinking about kind of what it's saying here, imagine the tangent line at that point. So we really wouldn't be able to actually find a slope at that point. Okay. And our last example here, f of x equals x to the 3rd. At x equals 0, again, the tangent is a vertical line. So this is the situation where we have a vertical line. So right at this x equals 0, so this point right here, this tangent line would be vertical, and that has undefined slope, so we actually wouldn't be able to find that. So these three last ones were just really examples of why you would be able to find derivative at a certain point. Okay, so just to kind of recap that, here's the examples of what the graphs would look like. Any sharp corners, any times that there's a cusp, anytime you have a vertical tangent, or again, what we just got done talking about in our last unit, we have vertical asymptotes, holes, and jumps. So this is a great little graph of all of those examples as to why it's not differentiable. Okay. Okay, so now we're actually going to review finding a limit. Okay, so let's take a look here. So we find the derivative given h of x equals 4 over x. Okay, so remember when we're finding the derivative, we could take the limit as h approaches 0 of the difference quotient. Okay, so when we find f of x plus h, we're going to replace the x in our original function there with x plus h, so that would be 4 over x plus h. Minus the original function, which is 4 over x, all over h. Okay, now how do we actually go about doing this? Notice again here, if we plug in 0, if I plug in 0 here, I get 4 over x minus 4 over x, so that becomes 0 over 0, so we get our indeterminate form. All right, so how can we get rid of this thing? Two different ways, right? You could subtract and then do your division. What I like to do again is I take a look at what I call these baby denominators, so the x and the x plus h, and that's what I'm going to multiply top and bottom by. So in the bottom, and the denominator, I'm again going to leave that hx, x plus h. I can always fill or distribute that if I need to, but in this case, I'm just going to leave it and determine if I need to do that later. When I distribute here, the x plus h cancels out, so all I am doing is taking x times 4, and I get 4x. When I distribute here, the x's cancel, so now I have negative 4, and I'm going to leave this right now as x plus h. So the x is canceled, so I take negative 4 times x plus h. Now we can distribute and start simplifying and see what starts canceling. So I'll have 4x minus 4h minus 4h. Again, make sure you bring through that negative. And again, I'm still not going to distribute in the bottom. I'm going to kind of take the wait and see approach. 4x's cancel. And then hopefully you even see here that this h would cancel with that h. So I would be left with negative 4 and then everything on the bottom. So I'd be limit as h approaches 0. And again, what's left here, what hasn't canceled, is negative 4 over x, x plus h. Okay. And again, if you need to see that extra little step there, so the negative 4x's cancel. Right, kind of squeezing that in right there. So what cancels here are these h's, which brings me to this step. Okay, so I canceled in a couple different fashions there. Now we apply the 0. So if I substitute that in, negative 4 over x times x plus 0. So then I get the derivative to be, this is literally just going to be -4 in the numerator, and then x times x, so I get that to be x squared. Okay. So now I know this actually isn't on your notes here, but I'm going to add something to that. Okay, so we just did this problem. Let me go ahead and put the derivative here, right? Here's the derivative we just found, so that's kind of part A, even though I didn't call that part A, so this is the derivative. Part B, find the equation of the tangent line to h of x at 1 comma f of 1. So we already know the derivative. We found the derivative and what we just did on the previous slide there. I didn't really call that part A, right? But again, we found the derivative. Oh, I'm sorry, it's h, not f. I can change that. This should be h. So we want to find now the equation of the tangent line. So what does the derivative give us? Well, again, the derivative gives us slope at a point. Some instantaneous point in time. Well, here's our point. So if we know our x value is 1, to find slope at x equals 1, we plug 1 in to our derivative. That would give us -4, which again is our derivative, which again is our slope. So we have slope at x equals 1 is -4. Okay? So if we write an equation of a tangent line, the tangent line is going to be a straight line. So again, we can do point slope form, which is y minus y1 equals m times x minus x1. Well, we just found slope to be -4, so we can plug that in. We also know x is 1. What we're missing, though, is our y value, because it says y value is f of 1. Well, how do I find this f of 1? Well, actually, that should be h of 1. I apologize. I keep putting f's in there instead of h's, because our original function is h. Here, right? Here's our original function. So that's exactly how we find that. We plug it into our original function. So h of 1 would be 4 over 1, which is 4. So our actual order pair is 1 comma 4, right? So that's the 4 that goes here. Now I didn't specify which form I wanted it in, point slope, slope intercept, so absolutely you can leave it this way. If you would like to FOIL it and add over the 4, you are welcome to do so. But again, you don't have to. -4x plus 8, this would also be okay. But again, that's point slope versus slope intercept. Either way is fine with me. Okay, you absolutely can leave it in this form. All right, so that wraps up day 2 of 2-1 in terms of difference quotient and our first day of finding derivatives.